trying to start going to the new building. It's a high honor for Nick to have this initial thing that he may be the final one in 15 years of distinguished seminarization. So anyway, so my pleasure to welcome Nick Laneman. Nick, a long time ago, was a grad student at MIT, maybe not that long ago. I think he's all well known to you for his paper and work on relay channels, but he's actually worked on more than that. So he's now an assistant professor for 3 years at Notre Dame, and he reports this morning that after the birth of his son, he realized, none of this is all that important anyway. It's nice that you're all here. So.
Thank you. Well, I don't think it's, not to oversell the talk. I don't think I meant to say that it was not important. I just view it as much less important than I used to since we've had our little guy. So it's a pleasure to be here. Thanks for coming. As Roy said, this is a little bit of a diversion from some of the stuff that I've been doing, and that's really largely because all this work is my students when he's gone. But I'll be talking about it today. So what we're interested in doing, the way I kind of came about this line of work is that, of course, we've learned a lot of things from an information theoretic standpoint about coherent fading channels. By the way, this term coherent is a bit sketchy. What I mean by coherent is that at least at the receiver we have channel state information, perfect channel state information, or fairly accurate channel state information about the fading process. Whereas maybe we know it at the transmitter, maybe we don't. But having that channel state information, an estimate of the channel allows us to do things coherently in the receiver. So we know a lot of things there, largely because we just kind of build on the classical work for the Gaussian channel. Whereas for non-coherent channels, or channels where we don't have accurate channel state information in the receiver, from an information theoretic standpoint, those are much harder to tackle. It requires an awful lot of machinery. You get these interesting results where you have a continuous channel, but the input distribution that achieves capacity is discrete, and so forth. So I sort of saw this wide gap, and I was curious to see if there might be something that, or we were curious to see if there might be something that fills it. And so at some level, it's really, in our view, it's really temporal correlation or even spatial correlation that fills this widening gap between these two extremes. And so while the results are not the results we have and some others have, they're not really precise. You don't get a nice closed form result like log of 1 plus SNR. For the capacity, we can bound capacity, we can see how it behaves in various regimes, and try to get some insights about different architectures for communicating over these systems. So one of the themes that's going to come out of this discussion today is that a useful tool is to think about transforming this otherwise more complicated channel into a simpler channel. And it's in particular a simpler channel that you can actually get some insights about. And we'll see how we do that in some different ways throughout the talk. So just to initially set some thoughts about the things I'll be discussing today, we're going to look at a scalar fading channel. So we have a single input, single output channel, additive white Gaussian noise, and flat multiplicative fading. And the key thing here is that we're going to allow that fading process to have a lot of memory in it, potentially. So it's going to be a correlated fading process. Some of the results that I'll actually talk about depend somewhat critically on this assumption that this fading process is circular complex Gaussian. So it's otherwise called a Rayleigh fading process. But the key sort of starting point, at least, is that we're going to start off without any precise channel state information about the fading process, either at the receiver or at the transmitter. We might estimate the fading using statistics of the fading, but we're not going to assume that that's readily available to us. So if you like, we're going to take into account the resources we have to spend to do channel estimation. And we're going to try to treat the problem from an information theoretic standpoint. So just to give you a sense of some of the work that's out there, you may be familiar with some of this stuff. I'll review a little bit of it as we go through. But if we take these channels and we sort of oversimplify things and break it into 4 regions, depending upon 4 regimes of operation, depending upon whether the fading is sort of really slow or fast, and of course that's a sort of nebulous distinction, right? Or whether or not this SNR is low or high, again a nebulous boundary here. there's been a growing body of work, and of course all I'm doing here is citing the stuff that is most relevant and most closely related to what we're talking about today. So basically, some of the early stuff for the fast fading channel, the memoryless fading channel, I referred to this before, that the input distribution for a memoryless Rayleigh fading channel is discrete. That was work done by Abu Faisal et al. There's also been some interesting work for ranges of signal-to-noise ratios and also both slow and fast fading by Lapedoth and Mosier, which says that in contrast to the coherent channel, where capacity scales is something like logarithmic with the SNR, for the non-coherent channel, at sufficiently high SNR, capacity sort of saturates into this log SNR behavior. Okay. There's also some work which is very related in terms of the structures of the systems that we're analyzing throughout the talk. This has just been submitted by Etienne and Shea, or it was submitted last spring, basically. So what the stuff that I'll be talking about is mainly, if you like, the story for the memoryless channel at low SNR is somewhat well developed. In fact, Abu Faisal did some numeric optimizations to compute capacity exactly in that regime. We know that you can get away with on-off keying, peaky on-off signaling in that regime. And for high SNR, when there's correlation, the results of both Lapedoth and Mosier and Etienne and Shea tell us a lot of the story. I'll try to review some of these pieces of work. The new stuff that I'll be presenting really lie in this diagonal of the matrix here. And so for slower fading at low SNR, we basically use a very similar type of encoding structure as what Etienne and Shea use. However, we restrict ourselves to phase shift keyed inputs, in particular circular phase shift keyed inputs. And that allows us to simplify the analysis quite a bit and get some insights in the low SNR regime. The other extreme, when we don't have correlation in the channel, as I said, there's a lot of results here. We can actually transform the channel into an equivalent additive noise channel, and we can sort of recast a lot of the previous insights that have been obtained in what we think are simpler and more intuitive ways. So I would say this is just sort of a recasting of some of the previous stuff. Although we do get a couple of new insights here. I should really emphasize there's been a lot of work on the so-called block fading channel model, and because we're focusing on continuously varying fading channels, all of that work is largely beyond our scope. So there's been a lot of important work there, but that's not as related as some of this work that I have cited here. Okay, so just to give you a rough sense of what I'll be talking about, slow fading at low SNR, fast fading mostly at high SNR is where our results are most interesting. Okay, so I guess I already summarized this. We'll start with slow fading and see how this notion of basically recursively estimating the channel using past observations and then treating the channel coherently with PSK inputs. We can actually essentially transform the channel into an equivalent coherent channel, and that's a useful thing to do for a fairly wide range of signal-to-noise ratios. For the fast fading channel, we can use this it's a logarithmic transform, and we get an equivalent additive noise channel, non-Gaussian noise, and so we'll say a few things about that model as well. So let's start off with slow fading. So we have to be a little bit more precise. We have to specialize our model some to indicate what we mean by slow fading. So specifically, we're going to have this, again, flat fading process. We're going to start off with a discrete time model. So we have a fading process H of k, our input signal S of k, and our additive noise Z of k. Just for simplicity, we'll normalize all three of these so that they're unit variants. So this leading coefficient here, rho, corresponds to the signal-to-noise ratio. Again, we have white noise, and the fading process, in this case, we're going to be varying quite slowly with respect to the symbol periods so that there's going to be correlation in the model. The way we're going to model that correlation is through the power density spectrum of the fading process. So it's a stationary process. We have its power density spectrum. And again, I want to emphasize that some of the tricks that we're going to be using rely on the fact that this is a circular complex Gaussian process. And we haven't quite extended all the results to more general fading processes at this point. Okay. So because there's correlation in the channel, it's sort of natural to imagine estimating the channel. And the classic techniques that are employed to do this are conventionally called pilot schemes, or pilot-assisted modulation, and so forth. there's somewhat, from an information theoretic standpoint, there's a bit of a dilemma here. And that is that typically these schemes insert training symbols periodically. The training symbols don't carry any information. They're used to only estimate the channel. And typically, the received signals corresponding to data, they're often not used to update estimates of the channel, because that introduces lots of correlations all over the place to make it quite tricky to do the analysis. The other thing is that there's sort of a tension here, because if you space the pilots close enough together to improve your channel estimates, you end up burning more and more of your degrees of freedom for pilots instead of sending information. Whereas on the other hand, if you space the pilots too far apart, then you end up with poorer and poorer channel estimates, which might end up affecting your performance as well. So there's really, in terms of a really large, complicated coding scheme, it's not really clear exactly how we should place our pilots in general. Of course, there's some work that allows us to do some optimizations here, but we're kind of trying to figure out what's going on from a more fundamental perspective for these channels. So there's nothing that says that this is optimal at the outset, right? So that's, I kind of summarized some of the limitations of pilot schemes. Of course, what's nice about pilot schemes is they give us this equivalent coherent channel where there's additional noise due to the estimation. But coherent channels, we can design the signaling schemes, we can come up with decoding algorithms that are tractable. The alternative is we sort of focus on non-coherent reception. And many of these non-coherent schemes, aside from, say, differential schemes, tend to be very tricky to analyze, and the decoder complexity can scale very quickly with the size of your encoders. So what we're trying to figure out is, can we kind of get around both of these issues in some way? And the answer is, if you're willing to spend lots and lots of delay, yes. Okay. So whether or not this is really practical, it gives us certain insights from a fundamental point of view. Whether or not this is really practical and can be reduced into a working system, I don't know the answer at this point. So how do we do it? What we do is we essentially do something like a differential scheme, but we do it in the code, not in the modulation. So let me see if I can explain this without mathematics, but instead with a picture. And by the way, this is not a new scheme. This has been around for some time. Shlomo Shammai pointed out to me that this has been around since the 60s yesterday. So, but I know Etienne and Shea use the same scheme. Andrea Goldsmith used some of these ideas in some of her work for finite state channels, and so on. So the idea is this: you have this fading process, or you can think of each one of these little cells here as a particular use of the channel, or a symbol period. So the fading process is going to be evolving in time here, and what I'm going to do is I'm going to construct a matrix out of the channel. Because it's a discrete time model, I can do that. So I'll fill in the rows in terms of the time, the evolution of the fading process. As soon as I get to the end of this row, I'll wrap around and continue and fill in this row, and so forth. What this allows me to do then is, instead, I can try to code my information vertically in this matrix. And if this matrix is wide enough, then the memory will vanish between this channel use and this channel use. So I create for myself a virtually memoryless channel here, vertically. And of course, this is nothing but an interleaver. I could think about doing some of this across time and frequency as well, but for the moment, it's just easiest to think about it in terms of interleaving. So I can think about writing my data, my coded data, into this matrix column-wise. I shoot it out onto the channel row-wise, and I do the reverse operation in the receiver, and that allows me to code over this essentially memoryless channel here in the vertical columns. So that's how I break up some of the channel memory. Now, how do I do training efficiently? What I do is, in the first vertical column here, I send nothing but training bits. Oh, by the way, this matrix is getting wide because I want to decorrelate the channel vertically. I also want this matrix to get tall so that I can get reliable coding across this parallel or this block of channel uses here. Okay, so here's where the delay is kicking in. I want to have a really, really wide and deep interleaver. So training comes in. What I do is I fill in this first column of the transmitted symbols as known pilot symbols. I send them over the channel. I use the received signals corresponding to those pilots in order to predict the fading in this column of the matrix. With that predicted channel, and I'm using, of course, the fact that between this channel use and this channel use, there's lots of memory. Using that prediction of the fading process, I can use the estimate in a coherent type receiver and just take into account the extra additive noise due to channel estimation, and then I can apply results for coherent channels. I have to be careful about the structure of that noise, though. So then I can, after I use a prediction of the fading process, I decode this block of data, and if I can do that reliably, then that block of data will be fresh pilot data, if you like, for the next block. And so at that point, I've got a whole new set of pilot data, and I continue along. Right? So it's a block decision-directed both training and decoding scheme. And because of this recursive nature to it, we call it recursive training. I may use this terminology parallel subchannel here. What I mean by that are the vertical columns of this matrix here in which we're actually putting our codes. Question?
What about error propagation in case you mess up the first time?
Great question. Error propagation. If I'm not careful about how I assign my rates or how I sort of prime the system, there could be error propagation here. What I'm going to do, however, is I might actually, instead of just using the first parallel subchannel here for training, I could use some block of, say, K of them, get the error, and what we're doing here is essentially Kalman filtering to do the estimation of the channel. I can get the error performance of the Kalman filter estimator to converge, or essentially converge, and from that point on I can transmit along at the same rate. Another possibility is to start off sending lower rates in these first channel uses where my estimation error is higher. So there's a bunch of different things that from a practical standpoint, if I really am concerned about tightening up the block lengths that I'm doing the coding, I can do power allocation, rate allocation to make sure I don't have that problem. For the stuff that I'm going to be discussing, I'm going to let the block length go to infinity, so I can always use, say, I can let K here go to infinity as well, the number of training periods that I use to bootstrap the system, but as long as K goes to infinity slower than the block length does, then the cost of training is 0 in terms of rate, asymptotically. Okay. So that's a good question. It's a good point. And we have to be careful about how we do the decoding here as well. We have to pick, because we're assuming that this block is large, we can make it arbitrarily reliable in terms of our decoding. Right?
Is K the length of your block? Code word?
No. What I meant by that is, you might say that the width here is L. Oh, I'm sorry. I said K just in passing. I see. K is the height here. So maybe I use the first M channels to do training instead of only the first channel. This first parallel channel here.
Well, after that it becomes decision directed.
Beyond that it becomes decision directed. Well, I mean, again, the point of information theory is not to show that the error probability of 0, it's to show that the error probability goes to 0 as you take various limits. And there's all kinds of little tricks you can play within this. I won't, we don't want to focus on all of them here, but basically, if you play with the epsilons and deltas properly, you can make it go to 0. Asymptotically. So, again, but we're not really too concerned about delay here. We're probably even less concerned about delay than the average information theoretic analysis is. So what happens with the additive noise? This is how our results and the work of Etkin and Shea basically differ. Okay? So what we're doing is we're estimating the channel. I've dropped all the time indices here just to kind of convey the idea. We start off with this fading process. You think about this as a particular use of the channel. We can write the fading as being its estimate plus some estimation error. Okay? We take the estimation error. That's also getting multiplied by S here, so all we do is regroup things together, and we're going to call this sum of the two terms. This is the original additive noise, and this is some noise due to channel estimation error in the system. You can think about this as sort of self-noise of our encoding scheme. What Etkin and Shea do is they say, well, we're going to look at, on a coherent channel, the inputs that achieve capacity are circular Gaussian, so we'll look at those. What makes their analysis much more involved is the fact that this noise is no longer Gaussian. This noise due to channel estimation error is no longer Gaussian. What we observed is that, well, if we're careful and we pick circular or proper phase shift keyed inputs, so we're only coding information in the phase, if the noise here, if the estimation error is circular symmetric Gaussian, then when we hit it with the PSK inputs, this term will be Gaussian as well. Now that's where we're relying on the fact that we have a circular Gaussian fading process. Okay. So essentially, now we have an equivalent channel, if you like, where it's a coherent channel because we know this estimate in the receiver, and our additive noise is Gaussian.
But it'll be correlated with your signal, right? Does that matter?
Well, it's not correlated. I guess I should put the time indices in here. This is a prediction of the channel in the current column of that matrix using information sent in the previous column. So that actually prevents it from being correlated.
No, we're thinking even if you have that, like, you're going to treat this second term as some kind of a noise. Is that what's happening? Like everything in the parentheses?
Yep, everything here is in the parentheses.
So there'll be a term, the H tilde D times S, right?
You're saying these two are going to be correlated?
Well, that is correlated with your, with the S over there.
And the same S is from different time.
No, they're the same.
Oh, wait, let's see. Let's be careful here. So, let me back up. Sorry. In the Gaussian case, my estimator is uncorrelated with the estimation error.
No, that I believe, yeah.
Okay.
But
so they're Gaussian and they're uncorrelated, which means they're independent.
Right.
When I take this, because it's phase shift keyed inputs, right?
Yeah.
I multiply these two together, and the input is independent of the fading process. I believe I can show they're uncorrelated, which in turn means, because they're jointly Gaussian,
Yeah.
that they're, I see your point. Your point is that this product is
normally your
correlated
additive
with that.
noise is independent of your signal, right? But in fact.
I believe we show that. Now you raise a good question. I just can't remember what the details are too.
Well, let's go along.
Okay.
The answer will come back.
Okay, so as I said, we convert the channel into essentially we're using decoded information as essentially as fresh pilots, and that allows us to continue estimating the channel. So let's summarize the results in the high SNR regime. Again, these are the results of Etienne and Shea mainly. They actually do a more general model where they're considering M input antennas and N output antennas. However, they do focus on a first-order Gauss-Markov process. So the particular correlation structure of the fading is specified there. Right? There is some games that they play with the limits. They allow the SNR to become large, while they also allow this innovation rate, which you can think of as the driving noise of the first-order autoregressive process. So this is the variance of the driving noise here. That's getting small. So the channel is slowing down. It's becoming more and more correlated. We're going to higher and higher SNRs. And they sort of break things down into these three regimes. And what's interesting is that, of course, you start off, you get something that looks like the coherent channel, where you have logarithmic performance in terms of signal-to-noise ratio. You also get the multiplexing gain of the multiple antenna system. Eventually, though, things saturate. You're still getting multiplexing gain, but you're limited by your channel estimation error. This is when your signal-to-noise ratio is quite large. It's larger than 1 over epsilon. Here, epsilon is a small number, so we're talking about very high SNRs. And finally, if you go to extremely high SNRs, and for some, realistic example scenarios, they talk about SNRs of 4 times 10 to the 4th dB. I mean, gigantic SNRs. You see this log-log behavior that is predicted by Lapidoth and Mosier's analysis. Okay. So the key thing is, in terms of practical situations, the key thing is you can approach coherent performance using this scheme. However, it does saturate at higher and higher SNRs. Yeah. Good question.
Did you say 40,000 dB?
4 times 10 to the 4th dB.
Okay.
Huge. In fact, I think actually it's 10 to the 7th. I have a note here somewhere. I can't remember the exact numbers. But depending upon epsilon, if I make epsilon small, epsilon can be on the order of, say, anywhere from 10 to the minus 2 to 10 to the minus 7. Right, relative to your symbol rates. When you look at cellular scenarios with a certain number of transmit-receive antennas, then you plug this epsilon in, you exponentiate, you take it to a certain negative power here, right? And then you exponentiate that, so it can be gigantic. So I mean, really, the point of this analysis is, well, I think one can interpret the point of this model and the results as saying, well, look, the log-log behavior does occur, but it occurs at unpractically high SNRs. okay, for a practical model, or for a first-order Gauss Markov model. So this is in the high SNR, mostly in the high SNR regime. When we use these phase shift keyed inputs, we can get some analysis, and we focus on the low SNR regime in general. So basically, a lot of this work, what it's relying on, both for Etkin and Shea's work and also this work, it's relying on a classic result of Doob for the convergence of a minimum mean square error estimator. So essentially, if you think about the estimator variance, the estimation error of our fading process, here infinity is denoting that we're essentially allowing is the time duration or the number of channels that we're using to estimate the channel in terms of remembering the past to do the estimation. That's getting arbitrarily large. So you can think of this as a causal Wiener filter performance or something like that. So you can write the performance of that estimator in terms of this interesting integral, exponentiated integral of the power density spectrum. And then, taking into account the fact that we have this extra additive noise, the effective signal-to-noise ratio after we do the recursive training is essentially this product here. What we've got is, this term is the power associated with the estimate. We don't have full fading power. We have to take off the estimation error. And then we have an extra term in the denominator, which is due to the estimation error itself. Okay? And that's multiplied, of course, by the signal power. This is under the normalization that we have, where the signal-to-noise ratio is equal to the signal power, and the variance is equal to 1 of the additive noise. So the point is, we can come up with a nice relationship relating the effective signal-to-noise ratio after we do all this decision-directed estimation and the underlying signal-to-noise ratio of the channel. So if we look at this a little more closely, we can find a couple different things. First of all, for a general fading process, so you tell me it's a nice wide sensationary process with a power density spectrum. As I let the signal-to-noise ratio get small now, okay, so in contrast to Shea and Etkin, we're looking in the low SNR regime. I let the signal-to-noise ratio get really small. We can apply a sort of a second-order expansion result that's due to Perloff and Verdue and find that the achievable rate that we obtain is as shown here. Basically, we have to have this integral of the square of the power density spectrum existing, and then what's important, the two things that are important, we get this leading coefficient in terms of this integral, and the performance is of order SNR squared. Okay? So that's quadratic behavior for a for a signal whose peak power is not getting large, right? So we have peak constrained inputs. However, it's known that we can actually get linear behavior, so the rate can behave linearly in the SNR if we use what Sergio Verdue calls flash signaling. So you can think of one example of flash signaling is I use on-off keying, but the probability that I use the on signal gets really small, and the power of that on signal gets really large. Okay? So relative to flash signaling, this basically at extremely low SNR, relative to flash signaling, this scheme is not performing very well using QPSK inputs in this training type approach. However, we could say, well, let's consider peak limited inputs. Right? You know, peaky signaling is not always easy to implement. So if we consider peak limited inputs, we can compare it to a bound. It'd be an upper bound on capacity here. It was developed by Hayek and one of his students. So under a peak power constraint, the capacity is limited by this integral here. Well, this coefficient in terms of an integral, rho squared. Okay. So what we see is that relative to the peak limited capacity at low SNR, this training approach using QPSK inputs is actually quite attractive. Right? The only difference is this factor of 1 here between the two. And we'll see this in a particular example in a second, but essentially the more narrow this power density spectrum is, the bigger this integral will be relative to 1. So the slower the process is varying, the better and better this approach looks relative to the optimal scheme, which is quite an involved scheme. What it essentially, I don't know if you're familiar with this result, it essentially uses on-off signaling, but it's vector on-off signaling. You use the on signal for a long time, and then you use the off signal for an even longer time. But you have peak power constraints there. So from the point of view of doing some coding, I think that this scheme is much, the scheme that Suthraman and Hayek work with is much harder to deal with than, say, coding for QPSK type channels. Okay, so the point again is the difference is of order half rho squared in this small SNR regime.
So I had a question. Is this,
Yeah.
I think it's related to what Maynard and Gallagher characterized by the correlated of the input distribution, right? They talk about the same notions of peaking.
That's right. That's why I say here, I don't know, I guess I didn't emphasize this, but this quadratic behavior for a peak-limited input is consistent with the bandwidth scaling results of Maynard and Gallagher,
Yeah.
and Hayek, one of his students, also has some results about this thing he calls the fourthity.
Yes.
Yeah. Okay. So again, relative to peak-constrained inputs, it turns out that this recursive training approach with PSK looks pretty good. To see this a little more explicitly, we can focus now on the first-order Gauss-Markov model that Etkin and Shea use. Okay. There, the spectrum is somewhat, relatively easy to compute. We compute this coefficient, it basically boils down to just 1 over epsilon minus 1. So again, as epsilon is getting smaller and smaller, this term will dominate the 1, and we'll be getting closer and closer to that upper bound of spectrum on Hayek. Again, here's this result that epsilon, for many practical scenarios in cellular systems, can go from anywhere 10 to the minus 2 to 10 to the minus 7. Okay? That's just a direct quote from Etkin and Shea. We can actually, for this first order Gauss-Markov process, remember I said we have the, oops, I went too far. We have this transfer relationship between the underlying channel signal-to-noise ratio and the equivalent signal-to-noise ratio. For the first order Gauss-Markov model, we can say a little bit more about that and get some results beyond just the low SNR regime. And so we get the following. We basically get 3 regimes as well. At really low SNR, we see this quadratic behavior in the underlying channel signal-to-noise ratio. For moderate SNRs, in particular between epsilon and 1 over epsilon, we see linear behavior in this transfer characteristic. So the effective signal-to-noise ratio is essentially the underlying channel signal-to-noise ratio. And similar to what Etkin and Shea developed, and also, by the way, what some of Lapido's earlier results suggest, when the signal-to-noise ratio is above this 1 over epsilon threshold, then performance saturates. The signal-to-noise ratio, the equivalent signal-to-noise ratio saturates because it's dominated by the estimation error. So you can plot this, and compare it to these are sort of linear slopes here. You can plot the actual transfer characteristic and see how things match. What's important is here we have epsilon being 10 to the minus 4. From essentially minus 40 dB to 40 dB, this channel is looking fairly linear, saying that over a broad range of SNRs, this coherent type, trying to transform the non-coherent channel into a coherent channel, which we've been doing for years in practice, right, is actually a pretty reasonable thing to try to do.
So the straight lines are from these
from this
asymptotic approximations,
right, from these,
right, and the little curves that are in the corners.
That's where at the regions, at the breakpoints themselves, we have the worst approximations. Is that true?
No, I'm just wondering, is that you calculated? Is that the result of
That's the solid curve is
this integral?
This.
Is this okay.
With the integral numerically computed.
Okay.
But in the first order Gauss-Markov case, it's just
All right.
it's much simpler.
Yeah. No, that's
Okay.
quite good. Oh, I guess somebody you'll say, oh, that's like a 4 or 5 dB or something. I didn't realize.
What's 4 or 5 dB?
Like it looks very good.
Well, these are
like some
these
normal
are really
signal
broad
signal.
ranges of signal-to-noise ratios, right?
Right. Got it.
So we could look at this a little more carefully, for example, and maybe we should really break it off here.
This is good. That's nice.
So this is about. Sorry. So this is the analysis that we can do. Just one thing to point out that we've seen numerically is the following. So we said that we're not doing as well at low SNR in terms of, if you like, capacity per unit energy, or rate per unit energy. If we take the amount of rate we get and divide it by the signal-to-noise ratio here, we expect to see 1 if we use peaky inputs as the signal-to-noise ratio gets really low. And just for comparison, on a Gaussian channel or a fading channel that's coherent, if I use complex Gaussian inputs, I do indeed get 1 as I go to low signal-to-noise ratios. What we're observing is that in terms of rate per unit signal-to-noise ratio, for this non-coherent channel with PSK inputs, we can actually get pretty efficient communications. We can almost approach the coherent case for not too low signal-to-noise ratio. At some level, this is consistent with the earlier results, but this is just a visual display of the capacity per unit energy. Things get better and better as the channel is more slowly varying, but eventually it tails off because of that quadratic behavior. But again, that's for I mean, I don't know how many systems operate at minus 20 dB and beyond. So, all right. So in other words, we're approximately linear. We don't have a coefficient of 1, but in this kind of regime, we can be approximately linear in signal-to-noise ratio with coefficients of order 0.7, 0.9, and so on.
So is UWB down there somewhere?
Well, it depends.
Where does UWB sit?
Faded? Isn't the not faded part?
Well, remember, the fading, we're assuming, has variance 1, so we've absorbed whatever. So this you want to think of as received signal-to-noise ratio.
It could be. I mean, 100 milliwatts is what I thought. It's even lower than that. You could have minus 20.
You could be that low?
There's no fading here. No, well, okay, so his results are, but somehow, right, like, there's definitely temporal variation.
Well, again, you know, pick your SNR, whatever it is. If the channel varies slowly enough, right, eventually these curves keep moving to lower and lower SNR regimes. So it's a trade-off between the signal-to-noise ratio at which you're operating and, you know, exactly how slowly the channel is behaving. Okay. So all those results that I described there were primarily were only for discrete time channels. So you might ask, well, what happens in the continuous time world? And I'll just try to give you a flavor of the result. Essentially, if we signal faster, it's essentially like we're sampling the channel faster, right? So from the point of view of our signaling, if we broaden our bandwidth, increase our signaling rates, we'll be sampling the channel faster, so we can make it look slower and slower relative to our symbol period. So the idea is that if I'm in the continuous time world and I broaden my bandwidth, I can make that loss associated, that subtraction of a -1 there, I can make that loss go away. And so more specifically, basically, if we take the same kind of limit, but now for the continuous time channel with peak power P per unit time, then this limit of, here we have the rate in bits per channel use, and this is the duration in seconds of a channel use. The limit as t goes to 0, you get this result here, which coincides exactly with Cepher amount and high X upper bound. Okay? So using more and more bandwidth slows the channel down relative to your symbol period. So there may be some implications here for ultra-wideband. There's a catch though. What I'm hiding, I'm not trying to hide it, the model is limited. I've assumed at the beginning, right, that it's a flat fading channel. Sooner or later, beyond a certain point, as I widen my bandwidth, that model will break down. And so we have to actually start over from scratch with a multipath channel model to actually say, perhaps we would have to say something about the multipath channel to get something in this ultra-wideband machine. Okay. But anyway, within this model,
right now in your column, like the fade values are all the same. I mean, that's essentially like your code. No, the other way around. Sorry. Yeah.
Across the rows, they flatten out.
Right.
If I can broaden my bandwidth, I can essentially make the channel look as slow as I like. But then again, multipaths start to resolve, and a lot of the assumptions that are in the model probably don't really hold in physical reality. But it's interesting to do this analysis, and another thing Shlomo pointed out to me is that a very similar result appears in Andy Viterbi's book, so I want to check that. He may have been looking at some similar things, because he did a lot of semi-coherent stuff back in the earlier days. Okay, so that's basically, oh, sorry, I forgot about this one. Should be paying attention here. Just to show you, this result here is for a general power density spectrum. As long as we have a wide sensationary process, we can plug in some well-known models here to see how they behave in this really low SNR regime. So here we have the first-order, continuous time first-order Gauss-Markov process, and here we have the Clark's or a Jake's fading model. There are some slight differences between the two at really, really low SNR. Here we have quadratic behavior. Here we have this extra factor of 1 over log 1 over the peak power. But that term doesn't kick in until extremely low SNRs. So these channels look pretty similar, even though one is band limited and one is not in this low SNR regime. So that's the story basically for slower varying channels. And the role of correlation, I think there's an emerging theme which from an information theory standpoint is more or less just validating what we've been doing for a long time, which is use the correlation in some way to estimate the fading and then try to use a coherent or at least a semi-coherent receiver, which is good because then again signal design and decoding algorithms are fairly easily developed. I mean, a key difference that's not here, of course, is periodic pilot training. Here we're using this recursive decision feedback type scheme to do the communication. So now there's a singular point in the model, which is when the fading process is not correlated at all. So it's a memoryless channel. For those types of channels, what we've been discussing so far, this idea of estimating the channel, is useless. So again, there's been a lot of work trying to characterize the fundamental limits of these channels, and it's required a lot of mathematical machinery, calculus variations, all kinds of very sophisticated stuff. And you get these curious results that, just one second, curious results that the capacity achieving input is finite and so forth. Go ahead.
So the other side is also singular from your coding perspective, right?
Which other?
Well, the flat fading. In the sense of
you mean
constant,
static fading?
Constant, yeah, static fading.
Static. Yeah, but you're saying if the coherence time literally goes to infinity, right? But we're actually not allowed. We're fixing epsilon in our analysis and varying signal to noise ratio. We're not letting epsilon go to 0. So in the fast fading model, basically what we've kind of happened upon is the idea that you can convert the channel into an equivalent additive noise channel, which we kind of think is, I find it interesting. So here we got to change the assumptions a bit. I dropped the time index because we have a memoryless model, so essentially from symbol to symbol we're assuming we have independent fading. Whether or not that's true in practice, it may not be entirely true. However, we might insert some additional interleaving to make it true. So that's the model that we'll consider. And basically there are two disturbances here now. We have two noises, a multiplicative noise due to the fading and an additive noise due to the underlying thermal noise. And there's been some work that basically says, well, take the absolute value of the output, take its logarithm, and then things break down. If the noise is small, then it essentially can go away and we have an additive noise channel. And the previous results that have been doing this, Rayleigh Chen and some of our co-authors, look at this in mainly the high SNR regime. Amos Lapidosa and his co-authors looked at this as well. What we sort of discovered is that in fact this kind of additive, not exactly this, but a similar additive noise model holds for all SNR. Okay? So essentially we combine the effects of Z and H into some other equivalent noise, and then we can develop some other insights about this channel. So just quickly to see how this comes about, because this channel, the phase carries no information. Again, we're focusing on Rayleigh fading here, circular symmetric Gaussian fading process. Because of that, the output, if I take the magnitude square of the output, it's a sufficient statistic for the channel. So there's no loss in forming this particular magnitude square. And this is a conditionally exponential random variable that's driven by the square of the input. So as a result, I might as well choose positive signals. So if I make a transformation now that I take the 1/2 the log of r, or in other words, just the log of the magnitude, and I look at the corresponding conditional density, this is our new channel if you like, what we see is that the input appears just as we take some function of the input and we shift it away from t, wherever t appears in this expression of the conditional PDF. So that's equivalent to saying that there's some additive noise in this channel. So in particular, we take the original fading channel, we convert it so we have a new output T, a new output U, and some additive noise W. U is just this transformed input. It's a positive signal, and the power constraint on the signaling turns into, the power constraint on S turns into a constraint on the moment generating function for U. The additive noise has this PDF, which looks something like this. It's an asymmetric noise, non-Gaussian noise. It decays much faster at positive values than it does for negative values. What we found, we've been trying to extend this model. We found that if we have and receive antennas and this independent fading both in time and in space, we can extend the model. However, we've been having some trouble when we have multiple inputs, getting an equivalent additive noise model. We think we have to have a bigger, the sufficient statistics have to be vector or matrix statistics in that case, and then it's not so clear how to take a logarithm there. Okay, so essentially we take the fading channel and we have an additive noise model. The key thing is it's an equivalent channel. We worked with that sufficient statistic at the output, right? If I give you any input S, I can find the corresponding input U. There's no information loss. But from the point of view, you know, if I want to do some signaling, I just make my constellation, drop down some of these additive noises, evaluate probability of error, and so forth. For example, one of the results in Tanabu-Faisal says that at low enough SNR, optimal signaling corresponds to on-off keying with different probabilities, not symmetric on-off keying. You can actually draw these plots and play with the error probabilities to see something similar like that from a modulation standpoint. It's kind of nice. It doesn't require all of this sophisticated calculus of variations to kind of see why that's true in this underlying additive noise model.
So the noise samples are, I'll ask like a good question here. The noise samples are independent from symbol to symbol?
Yes.
And so they're independent of you?
And they're independent of the input because of the shift in variance here. Those are the same properties you would see in a conditional distribution for a Gaussian, where you control the mean of the input, right? Or the mean of the output with your input signal. You can just think about this as you're shifting this this density depending upon this function, which we're going to call u. Okay. There's an interesting paper. It's a very short electronics letter paper, which was really the first paper to show at high SNR you get this log-log behavior. And it again develops a lot of optimization results, calculus variation results. We can get basically the same bound as a maximum entropy problem. In particular, if we write this mutual information, because it's an equivalent channel, these two mutual informations are the same. We know we can find the differential entropy of the noise, so all we have to do is maximize the differential entropy of the output, subject to the constraint that T is whatever you choose as your input plus this particular W. Now that's a hard problem. However, we can relax the problem such that we just meet some kind of expectation constraint, so that the mean of T is equal to the mean of U plus the mean of W, and we get exactly the same bound as Tarico and Elliott. So that's kind of interesting. The other thing that's somewhat interesting is we can get some nice bounds on the mutual information in this additive noise channel. Okay? In the additive noise channel, we can get an upper bound by assuming that the noise is Gaussian with the same variance. We can also get a lower bound on the mutual information using the entropy power inequality. And from these bounds, we can get some other conditions for mutual information to go to infinity. I mean, a big part of the work that Rayleigh Chen and her co-authors did was to come up with necessary and sufficient conditions for the mutual information of a non-coherent, or of a memoryless non-coherent channel to go to infinity. So we come up with some other conditions. They're actually very hard to relate between the two conditions, but basically we have both necessary and sufficient conditions for that. We can also come up with a condition to be asymptotically achieving capacity. We can use these conditions quite readily to check that complex Gaussian inputs do not achieve capacity at high SNR on this channel, which is already known, again. But all we have to do is check our sufficient condition. And the other thing we can do, because it's an additive noise channel, and the noise is, it's not exactly symmetric, but it's almost symmetric, you could think about doing pulse amplitude modulation in this additive noise channel, right? And I think we just did this as an exercise, and we discovered that if we do uniformly, a continuous input that's uniform on this channel, in the additive noise world, it's uniform. In the underlying channel, it's a Pareto distribution. We find that asymptotically, we achieve the capacity for the channel. So at high SNR, in terms of the asymptote. And we'll see some example plots of this in a second. In fact, here. So these blue curves are the results that we've developed for this channel model. As I said, there's been some other work. The original work that Abu Faisal did, again, numerically optimized the capacity by choosing these finite, these discrete inputs, both their locations on the axis as well as the probabilities that you use those. And unfortunately, that optimization gets a little dicey as you start to increase the signal-to-noise ratio. Because you have to add more and more points, it becomes more and more sensitive. So his results go out to about 10 dB in terms of that actual numeric computation. So that's his curve right there. The original Tarico-Elia upper bound on capacity is shown here. And lately, Labadoth and Mosier have tightened that result using this duality theory. And you can see there's quite a big tightening of that upper bound. The corresponding lower bound with their so-called fading number is shown here. So what we see from our results, this solid curve is the achievable rate of this log scale uniform input distribution. Okay? And these are our two this is our upper bound and our lower bound. What we see is that both our lower bound and the actual mutual information for the continuous uniform input is a better lower bound on the capacity than the Labadoth-Mosier bound. And actually our bounds, here at moderate SNR, our upper bound is quite tight, and at low SNR, our lower bound is quite tight for this particular input. The key thing to emphasize here is that this upper bound, from the point of view of doing anything with respect to capacity, is useless. Because this is an upper bound on the mutual information of a particular input. It is not an upper bound on capacity. Okay? But we just show it here to show that it is tight in various regimes, in case you don't want to do any numeric computation for this curve. Okay. The other thing we observed is that basically here down at lower and lower SNRs, you can see here's the capacity that's computed by Abu Faisal, and here is our curve with this continuous log scale input. There's quite a large gap. We know that asymptotically as the SNR becomes large, we achieve capacity. But at low enough SNRs, there's a pretty big gap here. This is on the order of 5 to 7 dB there. And what we've seen is actually we can use, instead of a full-blown continuous input, we just use PAM in this log domain. So we discretize and have a discrete uniform input. We have to pick the spacing appropriately to satisfy the power constraints. But interestingly, this set of input distributions was also motivated from the point of view of maximizing divergence, conditional divergence of the output given the input, by some guys from Rice. And just to see numerically how this looks, this dash curve here is the log scale continuous input. And if we use log scale, these are uniform inputs here, and so we're picking up several dB over this original continuous curve. We're still, far from capacity, extremely low SNRs, but in this sort of moderate SNR regime, we pick up quite a bit of gain by just discretizing the input. Which, again, is not surprising because Abu Faisal's result says that the capacity achieving input distribution is discrete, right? But here are some simple discrete constellations for which we could easily design codes and do our coding in this log domain.
Is it discrete uniform or like somehow maximum discrete?
So I picked a range before, and that range has to be determined by my power constraint.
Right.
Instead of being continuous over that range, I just pick discrete points and put probability masses there, compute the mutual information, and in these moderate SNRs, we do better in terms of achievable rates. Now, which scheme is better, depends upon the SNR. At low enough SNRs, binary is optimal, and as Abu Faisal shows, this is a symmetric on-off keying distribution here. Okay? Abu Faisal shows that actually an asymmetric on-off keying distribution achieves capacity at low enough SNR. But we can take the upper envelope of these curves and design, presumably we can easily design codes for uniform modulations and get reasonably good performance on these channels. Okay, so that's the story. Basically, again, for slow fading channels, what we try to do is get an understanding of how channel estimation should come into the equation, and both the results of Etkin and Shea and our results suggest that if the channel varies slow enough, you do want to do some channel estimation to get a coherent channel, or a semi-coherent channel. And we just also summarized this cute additive noise model for faster fading channels that may lead to more insights about these channels. We don't know. We've tried to get as many insights as we can from it, but unfortunately both sets of results seem a little bit fragile in the sense that if you change the fading just a little bit from that Rayleigh assumption, things start to break down. So we're still exploring that, trying to do some extensions, but unfortunately I don't have anything more to say in that direction at this point. So thanks for your attention.
You put this fixed interval and then you put uniform probability mass, then you get that thing called.
Sure. So you're saying the continuous one here? Okay, but just let me, again, this upper limit is determined by the power constraint. All I do to get the discrete uniform inputs is if you like, I combine some of these inputs into and make discrete probability masses that are uniformly spaced on this axis. There's a point at 0, and I uniformly space it up to this upper limit. So that's what this is stating. We pick this, the separation is delta here, and I have to find, depending upon the size of my constellation and the spacing, it has to satisfy this equation to satisfy my original power constraint.
The transform domain, after your channel transformation model.
Oh, precisely. Maybe I didn't emphasize that enough.
So in fact, there's some other sort of signal strength distribution that
It'll be transformed back. They'll be uniform. They'll have uniform probabilities, but they'll be exponentially spaced.
Yeah, right.
So, but Abu, for example, say that only non-uniform achieves capacity. Is that what it is?
He, in terms of, okay, so the statement is the following: a finite discrete distribution achieves capacity at sufficiently low SNR, and asymmetric on-off keying distribution achieves capacity. As far as I know, that's the only analytical statement that's made. He does do the, again, he's computing this curve here, and he also, along with this curve, which is his capacity curve, he shows a plot of how these new points come in and where their locations are and what their probabilities are. And as I said, it becomes a little dicey in terms of the numeric optimization. Did that answer your question? Or?
My question is, if you can get the capacity if you choose some other distribution, that question. Instead of the uniform.
He's saying, can you get closer to that curve rather than you're having then uniform probability?
Sure. So one thing we did, right, is we start off with this continuous model, which is easy to work with at high SNR. That's really why we talk about it. At low SNR, there's a gap. So we improve upon that gap, and there's not a huge gap there. There's maybe a dB in this kind of regime, right? However, as you really go down lower and lower in signal to noise, we don't know what we can say up here, right? Because we can't compute Abu Faisal's result up here.
Somehow I would have thought the gap should be easier to close down there because...
Well, it is easy to close in the sense that all we have to do is take this on-off keying. This is on-off keying in the log domain, right? Which, when we transform it, is on-off keying in the original domain.
Right.
All we have to do is change the probabilities that we use for them, and we'll get exactly this curve, because we know below, I can't remember exactly what the threshold is, but at sufficiently low SNR, asymmetric on-off keying, he shows it achieves capacity. The problem with that is that the peak power is large. So you're using, think of it, you're trying to code for a constellation where you use 0 with really high probability and 1 with really low probability. It's a little tricky to map linear codes onto that modulate. IID, by the way, it's a little tricky to map codes onto that. You can get away with sort of FSK type or PPM type modulations and wrap nested codes and things. But so in principle, of course, we can close this gap. We're just showing you how.
In fact, it's practice that's right. There's a good reason not to.
When we do symmetric binary, we can slap any linear code onto this additive model. We do it. I mean, I didn't really discuss it here, but we do show how you can do maximum likelihood decoding quite readily on this channel. Sure, you can always improve the performance at low enough SNR.
You should ask me.
Go ahead, what's your question?
So even in the transform domain, you have this peak power problem. Anyway, you are working in a transform domain, right?
Well, sure, but you're just taking the logarithm. So if the peak power is going to infinity in the original channel, the peak power is going to be going to infinity in the log domain, but it's just going slower. But see, the other thing is, remember, when you transform the channel, you also transform the power constraint. Right. So there's lots of things going on there.
So you got the T equals U plus W by ignoring the Z at the very high SNR, right?
No, that's the thing. We don't ignore the SO. We don't ignore the additive noise. This is just, this is basic. This is just, we just take some. Again, we recognize that this is a sufficient statistic. We take its logarithm, and the key thing is that this is an invertible transformation here, right? So I don't lose any information by transforming a sufficient statistic by an invertible function. And it's just so, my student came in one day and said, hey, I found this. I have no idea why, it's motivated by what was done previously, but he just happened to look at this particular conditional distribution and recognize that it's nothing but a shift here. And in fact, Shlomo pointed out to me yesterday that they knew of this when they wrote this. So Shlomo Shammai was on this paper with Ibrahim Abu Faisal. They knew of this. They developed a lot of their results using the additive noise model. They did not publish it. It was not in the final paper. There's one buried lemma where they state this. They didn't use it for signal design or try to get... I like this from the point of view that, hey, now it's an additive noise channel. And maximum likelihood decoding can be done. It's all relatively... it's both conceptually and mechanically simpler when you have an additive noise channel where the noise is independent. They didn't. It turns out in their published paper they didn't use this idea for much, as far as I can tell. What channels are fast fading channels? I don't know. Maybe you put wireless on a supersonic jet talking to a stationary something or other, and you might see this kind of behavior. I don't know. Most channels are slowly varying channels in practice, without interleaving.
Did you say that there was some results with the slow fading case that was known from the 60s?
The result, I have to look into this myself. Whenever you give a talk with Shlomo in the room,
right.
You sort of have to be prepared. And I think he gave me 6 or 7 references during the talk. He said this is exactly an equation that appears in a 68 either paper or book by Andy Viterbi.
Oh.
So I have to dig that up to find out exactly what the context was. In those days they were doing these wideband results to see what the minimum energy per bit was and things like this on fading channels. It could be something similar there, but I have to look that up actually. Okay, so
let's take a look at it.
I'll just mention if this stuff is of interest, we have this preprint about the additive noise stuff on the website. A preprint about this peak limited PSK stuff should be appearing on the website pretty soon. Thanks.
Thank you.